Hello, Professor Kevin. This is Chapter 9, Molecular Geometry and Bonding Theories. So, in order to determine the shape of your particular molecule, you first have to have the correct Lewis structure. Because when we design or when we name the shape, we use the theory of valence shell electron pair repulsion. And as I just said, we will be focusing on the central atom of your Lewis structure. Okay, so I'll repeat, we'll be focusing on the central atom. So if you don't have the correct Lewis structure, you don't know the correct number of bonds to the central atom, if you don't know the correct number of lone pairs, you will not get the correct valence shell electron pair repulsion, VSEPR theory. So here's a fictitious molecule where we have element A as the central atom. If we focus on the central atom, we have 4 domains, 1, 2, 3, and the 4th one here as the lone pair is considered a domain. And within the domain, we have 3 bonding pairs, 1 bond, 2 bonds. We consider this a bonding pair, even though it's a double bond. And we have 1 lone pair here at the bottom. Okay. The next one, we have 6 electron domains. 1, again, we look around the central atom. 2, 3, 4, 5, 6 electron domains, and we have 4 bonding pairs and 2 lone pairs. We treat the single, double, triple bonds the same as 1 domain. So let's try for water. So if we draw the correct Lewis structure for water, H2O. This is the correct Lewis structure for water, 2 bonding pairs and 2 lone pairs. So if you want to find the correct shape, you have to draw the Lewis structure, correct Lewis structure, step 1, and then you will count the number of bonding pairs and non-bonding pairs or lone pairs, and then you will, for now, refer to tables 9.2 and 9.3 from your textbook, or there'll be a table provided, but eventually you will have to memorize this for your exams. You have to figure out the shape of your molecule. So here's the landscape or the overall picture of the molecular shapes that you'll have to know. So we call on the left here the electron domains. We can kind of say the parent, and for instance this second one in trigonal planar, within the parent you have children. You can say trigonal planar here, which has no lone pairs and 3 bonds, and here next to it you have a bent shape. You have 2 bonding pairs and 1 lone pair. And we'll go through each one of these in the few slides following up. So coming back to the first example, we have our A as our central atom. We have 3 bonding pairs, and we have 1 lone pair. If we have 2 central atoms in our molecule, for instance, acetic acid, we treat each central atom separately. So the first one was on our table that I showed you, 9.2, was linear, and it makes sense. It's in a straight line. Our example is CO2. This is the correct Lewis structure for CO2. And if we focus on the central atom, linear molecules have 2 groups attached, one on the left, one on the right, and how many lone pairs are on the carbon? 0. So we have a linear molecule, and as the diagram shows, the angle is 180 degrees. Our second, we can say parent or electron group, is the trigonal planar. If we look at the trigonal planar, if we focus on the central atom, it has 3 groups attached, 1, 2, 3, and no lone pairs on the central atom. And as the name suggests, trigonal means triangle. It forms a triangle, and it's all sitting on one plane. So you can put it against the board, and all the molecules would touch the board because it's on one plane. Here's an example: CO or CH2O, formaldehyde. So here we have on the central atom, this is the correct Lewis structure. We have one group, two group, three groups attached, and no lone pairs. When you have three groups and no lone pairs, we say a trigonal planar. Within the trigonal planar, there's another example here. We have SO2. This is sulfur dioxide. So if we focus on the central atom, this is the correct Lewis structure. If we focus on the central atom, we have one group, two groups attached, and we have a third group, which is a lone pair. So when you have two bonding pairs and one lone pair, we say this is a bent molecule. The third type is a tetrahedral. Tetra means four. You guys remember in Tetris, you get four in a row. We saw that at Tetris. So a tetrahedral, we call that four sides. There's a side on the left. There's a side facing us. There's a side in the back. And then there's another side, a fourth side underneath. So that's a tetrahedral shape. If there are four groups attached, in the example of CH4, if there's four groups attached and there are no lone pairs, we call that a tetrahedral, and the angle is 109.5. We have a trigonal pyramid. Here we have three groups attached to the ammonia, to the end, three groups attached to the end and one lone pair. And this forms a pyramid, as you can see, and it's a three-sided pyramid. So we say trigonal pyramid. And the reason why the angle is a little bit less, 107 degrees Celsius, sorry, 107 degrees, as opposed to 109.5, it's because of this lone pair up top. Lone pairs and bonding pairs, there's some repulsion between the two, so it's going to push down the NH bond. If it pushes down, the angle gets smaller to 107 compared to 109.5, and I'll touch a little bit about this in the next slide. We have here a bend shape. Water is an example. If you guys recall, water, H2O, we did this already. It has two bonding pairs and two lone pairs, two bonding pairs and two lone pairs. In total, the electron domain, there are four around the oxygen. But when you have two groups that are bonding and two lone pairs, we call this a bent shape as well, similar to the SO2. The SO2 had two groups attached, two bonding pairs, and one lone pair. So as I mentioned in the previous slide, there is an effect when you have a lone pair. The theory, valence shell electron pair repulsion. And as you know, electrons, they repel each other. If they're negatives and negatives, they repel each other, as opposed to a positive and negative where they attract. So in this case, as we compare the trigonal planar on the left, it has no lone pairs on the central atom. But if we look here, the example we used was ammonia. Here it has a lone pair on the central atom, and the repulsion increases. So if you have a bond pair and a bond pair, so if we compare these two, there's not much relative repulsion. If we add, compared to a lone pair and a bond pair, the repulsion forces increase. So this repulsion here between the lone pair and the bond pair increases. And in the case of water, it has two lone pairs. Those two lone pairs repulse the greatest amount. So there is a sequence of repulsive forces. When you increase the amount of lone pairs, in theory, the repulsion should increase. So what are the three we talked about up to now? We had a linear shape, which has two groups, two bond groups, and no lone pairs on the central atom. We talked about tetrahedral, which has four groups attached and no lone pairs. We talked about trigonal planar, which has three groups and no lone pairs. And we talked about bent, which has two groups and one lone pair, or two groups and two lone pairs. So we continue on with the next one, which is trigonal bipyramid. If we look at the name, trigonal again means a triangle. Bi means two, so there's two pyramids. In this case, we have a pyramid above the plane, and we have a pyramid below the plane. So three-sided pyramid above and below. And to determine if you have a trigonal bipyramid, if we look at our example here as arsenic pentafluoride, if we focus on the arsenic, we have five groups attached and we have no lone pairs, which results in a trigonal bipyramid. The next example is iodine tetrabromide. So if we focus on the central atom, we have four groups, 1, 2, 3, 4 groups, and one lone pair. So we can think of this as a seesaw. That's the name of the shape. We have here the pivot point with the lone pairs. We can look at it in that view. So when you have four groups and one lone pair, we call it a seesaw. Those belong to the parent trigonal bipyramid electron domain geometry. Some more trigonal bipyramid, we could say children. Another one is a T-shape. The example here is chlorine trifluoride, where we focus on the central atom. This is the correct Lewis structure. We focus on the central atom. It has three groups, bonding groups, 1, 2, 3, and it has two lone pairs. And this results in a T-shape. So these are some ways to remember, some mnemonics to remember. The next one is linear, where we have here two groups and we have three lone pairs, 1, 2, 3. So in this case of xenon difluoride, this would be a linear shape. The three lone pairs will space out so that the two bonds, the F, will form a linear diagram. And this is a 180-degree angle as well. We go to the fifth electron domain geometry, octahedral. Octa means 8. So here we have 8 sides. We have 4 on the top, 1 towards us, 1 to our left, 1 to our right, and 1 behind us. So there are 4-sided on the top, and there's 4-sided underneath as well to make a total of 8. The example here is, well, octahedral. Again, when you have 6 groups and no lone pairs, 1, 2, 3, 4, 5, 6, and no lone pairs. And the other example is a square pyramid. So here we have 1 lone pair below. It can be above as well. And we have 5 groups attached to the iodine in this case. 1, 2, 3, 4, 5. So a square pyramid. And to continue on, we have something called a square planar, which is again from the octahedral parent group. A square planar consists of 4 groups, 2, 3, 4, so 4 bonding groups, and 2 lone pairs, which coincides to give us a square planar. You can see the square here on one plane in the molecule. So coming back to the original table we showed you, so if we looked at the linear, the only one that you can have is a linear. 2 groups and no lone pairs, trigonal planar. It has 3 groups, no lone pairs, or 2 groups and 1 lone pair. The tetrahedral, which is the parent, you can have again no lone pairs to give us a tetrahedral. You could have 3 groups and a lone pair, 3 groups and a lone pair to give us a trigonal pyramid such as ammonia or nitrogen trichloride. We have here the water molecule, which is bent. We have 2 bonds and 2 lone pairs. Come down here for the 5th case with trigonal bipyramid, which is 5 groups and no lone pairs. We can have 4 groups attached to the central atom. We're always looking in comparison to the central atom. 4 groups and 1 lone pair, which is a seesaw. We also have a T-shape, 3 groups and 2 lone pairs to give us a T. And we also have a linear where we have 2 groups, 2 bonding pairs, and 3 lone pairs, 1, 2, 3, to give us a linear shape. And for octahedral, we have the octahedral. We have the square planar, which is, square pyramid. Here's our pyramid. And we have a 1 lone pair attached to the central atom. We have square planar, 4 bonding groups. Here's our plane. And we have a lone pair above and below. And we have a T-shape, which we did not talk about, I believe, but it's 3 bonding groups and 3 lone pairs attached to the central atom. Quite a lot of information, but let's try to put this information together. We drew these Lewis structures in chapter 8, so I will quickly go through them, and then once we have them in front of us, we will focus on trying to determine the shapes. So again, you can try on your own first. I'm not going to count the number of valence electrons. Hopefully we've done this already. And I'm going to focus just on the central atom. So I'm not going to put the lone pairs for the electrons around the outer elements. Number 4, well, let's just do the first 3. Here we have water, we talked about already. We have 2 groups attached, 2 bonding pairs attached, and 2 lone pairs. So when you have 2 bonding pairs and 2 lone pairs, that should trigger bent shape. The next one for nitrogen trifluoride, we have 3 groups, 1, 2, 3 groups, and 1 lone pair. So 3 groups and 1 lone pair corresponds to a trigonal pyramid. And the last one, we have carbon tetrachloride, 4 groups attached, no lone pairs. That gives us a tetrahedral shape. Let's continue on. Number 4. Again, we only focus on the central atom, but I'll draw this. And here we have 4 groups and no lone pairs, so this is a tetrahedral. In this case, we have 2 central atoms, so we focus on the carbon on the left first, call it C1 and C2. For C1, we have 2 groups attached, 1 group, 2 group, and no lone pairs, so we call this linear. For carbon number 2, we have 1 group to the left, 1 group to the right, so we have 2 groups and no lone pairs, so that's linear. If they're both linear, the whole molecule is linear. For number 6, we have the C. So in this case, we have one group on the left, one group on the right, no lone pairs on the central atom. So this is a linear molecule. And the last one, NH4, it has 4 groups and no lone pairs. This is a tetrahedral. So I believe questions 8, 9, 10, and 11. We didn't draw these Lewis structures yet, but let's give it a try. On the next slide, I'll quickly go through this. Sulfur hexafluoride. If we focus on the central atom, there are 6 bonds and no lone pairs, so this is a octahedral. Number 9, I3 minus. And we count the number of valence electrons. It is 7 for one iodine. So 7 times 3 is 21, 22. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We only focus on the central atom. So the central atom has 2 bonding pairs, 1, 2 bond pairs, and 3 lone pairs, 1, 2, 3. And this coincides to give us a linear shape. Number 10, which is C. It's a double bond there. We focus on the central atoms. C1 and C2. C1 has 3 groups attached. 1, 2, 3 groups attached and no lone pairs, so it's a trigonal planar. And the carbon on the right has 3 groups, 1, 2, and 3 groups to the central atom, so that's also trigonal planar. So overall, it's a trigonal planar molecule. Let's look at the last one, which is acetic acid. I'll draw the Lewis structure. H, 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 and carbon, double bond, O. So if we look at each central atom, the carbon on the left, it has 4 groups attached to it and no lone pairs, so that's a tetrahedral. The central carbon has 3 groups attached and no lone pairs, so that is a trigonal planar. And the oxygen on the right is also a central atom. It has 2 groups and 2 bonding groups and 2 lone pairs, so we call this a bent shape. So we first just showed you how to do the Lewis structure, then we figure out the shape, and the third property we want to give it is to determine whether your molecule is polar or non-polar. And there are 2 factors. One is bond polarity, which we talked about a little bit about the electronegativity differences. If it's greater than 0.4, it is a polar bond, and then we just talked about in the previous few slides about molecular shape. So there are 2 factors to determine if your molecule is polar or non-polar: bond polarity and molecular shape. So we already talked about polar bonds. You need the electronegativity table in front of you, or it needs to be given to you, the electronegativity values. The fluorine is the most electronegative, the cesium is the least electronegative. Fluorine is, I believe, 4, cesium is 0.7. So in this case, we do the comparison. We subtract the higher one from the lower element to figure out if it's greater or less than 0.4. We also have to consider the shape. So in this case, we have here NH3. It has polar bonds. The N is more electronegative than the H. The electronegativity difference is 0.9, if you remember. So the N is more electronegative, so the vectors will point towards the N, and there's an electronegativity difference here, as I just said, and it points towards the N. So within the bond, the electrons spend more time around the nitrogen. So this would be a polar molecule. A nonpolar molecule. So in this case, we compare the B and the F. These do have polar bonds. F is the most electronegative element. It pulls the electron in this bond pair towards the F. So there are polar bonds in this molecule. However, because of the shape, we know this shape is a trigonoplanar, which it has 3 groups and no lone pairs. They pull each other evenly. So when you pull evenly, there's no net, you can say no net polarity. They all cancel out. So overall, the molecule is nonpolar. So for BF3, boron trifluoride, you have polar bonds. However, they cancel each other out because of the shape, and you have a non-polar molecule. In this example to the right, we have CCl4. Again, we do have polar bonds between the carbon and the Cl. We know this from the electronegativity table differences. It's greater than 0.4. However, because of the shape, it's a tetrahedral. The chlorines pull evenly in all directions, so they will cancel each other out. If I had replaced, let's say I had replaced this Cl, and let's say I put an H here, so now there's not an even pull in all directions. So in this case, this would be a polar molecule, CHCl3. It has polar bonds, and they don't cancel each other out, even though it's a tetrahedral. So let's take a look at the CO2. This is the correct Lewis structure. The shape is linear. If we want to determine if it's polar or nonpolar molecule, the electronegativity difference is 1. If you guys recall from our trend, F is the most electronegative, but O is located here, and then C. So O is more electronegative. So it's going to pull a bit more to the right and pull evenly to the left, so they cancel each other out. Just going back, if you remember the trend, the most electronegative is in the top right, and the least electronegative is in the bottom left. So they pull evenly to the left and the right, so they cancel each other out. So CO2 has polar bonds, but overall it's a non-polar molecule. Because of the shape, they cancel each other out. Let's take a look at the question here. CH4, is it polar or non-polar? The difference between the carbon and the hydrogen is 0.4, so it's a non-polar bond. And they also cancel each other out, so this would be a non-polar molecule. If we replace one of those H's with a Br, this would become a polar molecule, and they would pull towards the bromine. So let's go back to our examples. We know with the water, it has polar bonds, and also because of the shape, it's a bent shape. So let me redraw this, bent. This is a polar molecule because the pull is towards the oxygen in both cases. So it's a bent molecule. The vector goes up. So polar molecule for water. for NF3, so I'll give you guys a hint here. If there is one or more lone pairs on the central atom, right away this will be a polar molecule. I'll repeat. If there's one or more lone pairs on the central atom, you have a polar molecule. There are some exceptions, of course. The square planar, which has 2 lone pairs and 4 groups. If they have identical bonding groups and 2 lone pairs, this would be a non-polar molecule. Another example is a linear. When you have 2 groups, 2 bonding groups attached, and 3 lone pairs, this gives us a shape of a linear. If the 2 groups, bonding groups, are identical, this will be a non-polar molecule. But in general, if you have 1 or more lone pairs on the central atom, it is a polar molecule. So in this case, this would be a polar molecule as well, because there's 1 lone pair on the nitrogen. For CCl4, this would be a non-polar molecule, because even though the chlorine-carbon bond is polar, they cancel each other out. In this case, number 4, you have 1 F and 3 H's. So you do have polar bonds. It's towards the fluorine. So this would be a polar molecule. Number 5, this would be a non-polar molecule. It has non-polar bonds, non-polar molecule as well. And number 6, this would be SCN. This would be a polar molecule because the poles between the left and the right are not identical. So this would be a polar molecule. And for NH4, this would be a non-polar molecule because the H's, or sorry, in this case the N's, will pull identical towards the N in all directions, so they would cancel each other out. So let me erase this. Hopefully you guys have tried number 8 to 11. You can try 1 or 2 while I erase. So for SF6, we have S in the middle, and then we have 6 groups attached to it. The octahedral, they will cancel each other out. So SF6, 1, 2, 3, 4, 5, 6. There are no lone pairs on the central atom. There are polar bonds, but they cancel each other out. So overall, this would be a non-polar molecule for SF6. Number 9, we talked about already. When you have 3 groups, I said if you have 2 groups and 3 lone pairs, it's a linear molecule. If the atoms on the left and the right are identical, this would be a non-polar molecule. For C2H4, it's a double bond. So here we have a non-polar molecule because the C and the H and the C and the C are non-polar bonds. So we have a non-polar molecule. And for the CH3COOH, so this is the CH3COOH. So in this case, we look at each central atom. The carbon on the left would be polar. The carbon in the middle would also be polar. There's a stretch towards the oxygen. I'm sorry, on the left it would be non-polar. So let me write this non-polar because you have hydrogen and carbon, which is a non-polar bond. And to the right you have carbon and carbon, which is a non-polar bond as well. And for oxygen, you have a polar bond, and you have a bent shape. So we have polar going from left to right, nonpolar, polar, and polar. Overall, this is a polar molecule.